phase type distribution and this kind of stuff, but I'm starting with very basic notions. So I'm going to talk about structured Markovian arrival processes. This is a joint work with Sophie Houtfen and Yoni Nazarati, and starting with phase type distributions. We know that in a simple way, the phase type distribution showing the distribution of the time that it takes for a Markov chain with one absorbing state to go through that absorbing state. The parameters that we have are eta, which is the initial distribution of the Markov chain. From now on, we call it the phase process. Here in this example, we have 4 phases. And then we have the matrix T showing the transitions, the transition rates of going from these 4 states to the transition rate between these phases and actually the transition rate for this Markov chain. In 1975, Marcel Nutz, the founder of this workshop, gave the structure and mathematical background for a phase type distribution in terms of a new matrix A, which is actually the first row, which is all zeros, showing that the process from the absorbing state doesn't go to any other states. And then this is the matrix T, and this little t is called the exit vector, showing the rate of going from the phases to the absorbing state. And I forget to say that this p here shows the number of phases that we have. In this example is 4. Using phase type distribution, we can have many examples, familiar examples of the distributions that we know. For example, exponential distribution has the structure of phase type distribution through eta and a, which is given here. Also, sum of exponential distributions or airline K distribution has a phase type distribution with this structure. And convolution of exponential distribution or hyperexponential distribution is another example of phase type distributions. As you know, for airline K, the squared coefficient of variation is less than 1, and for hyperexponential is greater than 1. And actually, we can show that we can approximate any distribution with the support on the positive line with the phase type distribution, and this is the importance of working with phase type distributions. Now, if we consider a counting process when the interarrival times are identically independent and identically distributed based on a phase type distribution, then we have a phase type renewal process. I forget to remind you about the color that I used. If I go back here, whenever I have transition only between phases, I show it with blue one. And whenever I have transitions accompanied with an arrival later on, I show it, or going to the absorption, I show it with the red one. So that's the reason for the colors. Here I consider the blue ones here. And the reason is that what happens during the interarrival time is that we have transitions only between phases, and whenever the process goes to the absorption state, we have a new arrival. Now, if instead of considering independency between interarrival times, I consider that they are dependent on each other, I can introduce the Markovian arrival processes. So here I show a different diagram to showing Markovian arrival process. For the case that I have 2 phases, the vertical line shows the level or the number of arrivals, and the horizontal one shows the phase. So here we have phase 1 and then phase 2. The blue one showing transition only between phases, and the red one shows transitions accompanied with an arrival. Looking at the matrix A in this case, we see that it has a structure as a bidiagonal matrix. The elements on the diagonal showing are the block matrices showing the transitions which only between the phases, and the upper diagonal elements are all matrix elements of matrix D, showing transitions that are accompanied with an arrival, or the red ones that you can see in the figure. One famous example is Markov modulated Poisson process, which is a doubly stochastic Poisson process. This is here again considering we have two phases, but in general case, we have finite number of Poisson processes. We have some transition in the phase process, the blue ones here, and whenever the process here is in phase one, the process of having arrival is like a Poisson process with rate lambda 1, and whenever we are in phase 2, it's like a Poisson process with rate lambda 2. Looking into matrices C and D in this case, we can see that because we don't have transitions from here to here or from here to here, the matrix D is actually a diagonal matrix, showing just the elements of the rate of the Poisson distribution that we have for phase 1 or phase 2. When we talk about the stationarity of the Markovian arrival process, actually we have two kinds of stationarity. One is related to considering the inter-event or inter-arrival process, and which is known as the event stationary. Briefly, it says that if we consider n consecutive, the distribution, joint distribution of n consecutive inter-arrival times, and we move them during the time, this distribution doesn't change. And if we look at the counting process, n of t, we can talk about the time stationary process when we consider the distribution of number of arrivals during fixed interval of time with length s, and we move it in time. This distribution doesn't change. In terms of matrices C and D, or actually parameters of map, event stationarity happens when the initial distribution is alpha, which is given by as a unique solution for this equation. And the matrix P here actually is the transition probability matrix of the jump process that we have. For the time stationary case, the initial distribution should be equal to pi. I think you are most familiar with, I know that you are all familiar with this one, just if, as a reminder. Here pi q equals to 0. I use all the vectors as a column vector, and whenever I have a row vector, I use the transpose of that. The matrix Q here is sum of the matrices C and D. The other thing that I use for my calculation is deviation matrix. We have a transient deviation matrix, which is given by this integral. And whenever t goes to infinity, we have the deviation matrix. There are some properties of deviation matrix. For example, if we multiply it with column vector of 1, the result is a column vector of zeros, or pi times that give us 0. And if we multiply it with q, it can commute, and we have this result. The deviation matrix first introduced with Cullen and Van Dorn in this paper. And I tell you why I need it later. Also, there are some important integrals that are used in my calculation. And as you can see, they are mainly based on the deviation matrix or transient deviation matrix. Are you familiar with these integrals? Use them in your calculation? Yes, I think these two ones, which are in the Asmussen's book, are the most that you are familiar. But in Asmussen, instead of deviation matrix, he found them in terms of the fundamental matrix, which is inverse of 1 pi minus q. But we can find deviation matrix and transient deviation matrix in terms of this fundamental matrix. Okay, the main story is that I think most of you know that during my PhD, about 8 or 9 years ago, I started working with some subclasses of Markovian arrival processes and relation between them. The result was a paper with Sophie and Yoni. We tried to submit this paper around 2019 or 2020, but we didn't successful. About 1 year ago, I decided to back to that paper and try to revise it and resubmit it again. So I tried to make myself again familiar with the techniques that we used for that paper. And I don't know if you say that I use Asmussen's book as a Bible or as a dictionary. So I use it for all of my calculation, but I found that something doesn't work. So I started to working through all the calculation in Asmussen's book. And then I don't know, I was excited because Asmussen is a very big person, but I found the typo in the paper, and that was the reason that I have some mistake in my calculation. The typo actually was related to this integral. And it was the motivation, as I told you, to do all the calculation for myself. So in the time stationary case, I started to find the conditional n factorial moments of the number of variables, given that the process at time 0 is in a state I, and after time t is in a state j. In Asmussen book is actually given based on the this is the normal way of finding that based on the differential of the generating function, and this generating function in terms of matrices C and D can be given by this. The result was that we could find this kind of recursive Sylvester equation that gives mn of t in terms of mn minus 1 of t. And then we can find mn of t in terms of this integral of mn minus 1 times dEq. This one is actually given in the Asmussen book, but we show that we have an equivalent with that, which is this one. And explicitly, we can find mn of t as this multiple integral. It's 2 pages of proof for this proposition. Then I back to what I've had in my previous work. I wanted to compare the moments, the factorial moments of the time stationary case for different Markovian arrival processes. So I needed to find at least the first 3 ones. The first 2, you can find them in Asmussen book and some other papers. But the third one is the new one that we found in terms of deviation matrix. Based on that, we can find the case of the first factorial moment in case that we don't have time stationary case, which is given by this one. And the variance, which is variance, is actually the one that's given in most of the papers and in Asmussen book in terms of deviation matrix. Now back to the structured maps that I work with them. So I consider the whole map and 2 subsets of them, Markov modulated Poisson process and Markov switch Poisson process, and then some subclasses of them. And then I show that, I'm going to show that these 2 subsets can consider as the equivalent of each other in terms of the first and second moment. So back to the Markov modulated Poisson process, just look at the matrices C and D. The matrix D is diagonal in this case. If I'm going to Markov switch Poisson process, this is a Markovian arrival process when all the transition in the phase process accompanied with an arrival. So in this case, we don't have the blue transitions just between the phases, and as a result, the matrix C can has a form of diagonal matrix. Again, here everything is for the case that we have only 2 phases. A subclass of them is what we called Markovian transition counting process. So comparing with the previous one, we don't have this type of transitions in without change of the phase. So any transition, or actually whenever we have an arrival, we ensure that there was a transition or change in the phases of the phase process. And as a result, in addition to having matrix C as a diagonal matrix, we have 0 in the as the diagonal elements in the matrix D. Now, back to when I started in my PhD, it was actually based on a paper with Yoni and Gidenvis. The idea comes from this paper, and this is actually the revised version of that. For any time stationary Markovian transition counting process with order P, we can find an MMPP with the same order, which has when these two processes have the same first and second moments of the counting process. The interesting thing is that these two processes are kind of extreme cases of the Markovian arrival processes. In one of them, whenever we have an arrival, we ensure that there was no change in the phases of the underlying process. But in the other one, whenever we have an arrival, we ensure that there was a change in the phase process. But the first and second moments are the same. So the question was that, can I find the other way? Can I find for any MMPP an equivalent MTCP with the same order? The proof for this one is 2.5 line, let's say 3 line. And then I try to find something for the inverse of that. So what I found is that for a time stationary MMPP, if we have a time stationary MMPP with order P, with this condition that lambda I is greater than sum of Tij's, means that if I consider the two cases, the rate of having arrival from each phase is greater than the sum of rate of going from that phase to other phase. We call this kind of MMPPs, the slow MMPPs, and most of MMPPs that's used in application are actually in this category. So for this kind of MMPP, I can find an MTCP with the order which is double, with the order 2p, in the way that the counting process, if I consider the moments of the factorial moments of the counting process, they are the same for the first and second moment, but they are not the same for the third moment. What's your guess about the proof of this? How many pages? It's about 5 to 6 pages of proof just for showing this proposition. I just show you the idea here. The idea is that, okay, I have here, for example, I have an MMPP2, and then I want to compare it with MTCP4. I just make it kind of couple like this to make a map with the same order and the same factorial moments, and then I compare this one with the MTCP2P. So actually, I show that the first and second moments of this map is the same as the first and second moment of this MTCP2P. And this is the part that Sophie helped when I have the proof for the case of 2 phases, and I wanted to extend it for the general case of P. Actually, Sophie helps with doing part of the calculations. Okay, so far we have these maps. I just introduced them in terms of the matrices C and D. For MMPP, the matrix D is diagonal. I think I should show this circle a little bit bigger because it's considered most of the maps. Then I go for SMPP, slow MMPPs. in the matrix C, I have this condition. And then for MSPP, I have a subclass MTCP, and then another subclass, which is the matched MTCP Markovian transition counting process, which is the MTCPs when the order is even. And then the first and second moments of these two are the same. The other thing is that what happens if we don't have a time stationary case? If we don't have time stationary case, actually we can show that for the slow MMPPs and the class of matched Markovian transition counting process, the first factorial moment still remain the same, but we don't have the second or third moments the same. And I think I was very quick. The future work is actually considering the minimal Laplace still just transform representation of these various classes of maps. And we believe that if we go to the subclasses of these maps, we need fewer parameters to introduce those maps. And that's actually the reason that we want to do, we are in the middle of doing this. And the reason is that this is one way of showing that MTCP or matched MTCPs could be better than SMMPPs because we need fewer parameters to showing them. Okay, thank you. That was all.